Okay, Alexander is a role software engineer at Nature Robotics. He completed his PhD recently at Osnabrück University, so congratulations to him.
Thanks.
He's been working on ray tracing-based simulation and probabilistic localization navigation using triangle mesh environment representations. We got in contact for the first time, I think, after a talk about Beluga in Odense 2024 in Roscoe. And since then, we have remained in contact over our shared interest in localization. He has a number of very interesting projects in this area, and he was kind enough to join us today to present this talk, MeshNav, Any Terrain Navigation. So, Alexander, I will leave it to you.
Yeah, thanks for the introduction. I'm very happy that you invited me here. So today I will tell you something about the whole ecosystem about our mesh navigation project. So yeah, as you said, my name is Alexander Mock, and because I'm pretty sure that not so many people know me, I will start to introduce myself. That's me, with a bit shorter hair. I'm 31 years old, and I'm a PhD in computer science with a focus on robotics. Yeah, until last year, I did my PhD at Osnabrück University on LiDAR simulation and probabilistic localization. I'll tell you a bit more later on that, because it's influencing a bit this mesh navigation ecosystem. Yeah, and now I'm a robotics software developer at Nature Robots. That is a company writing software for agricultural machines so that they can get autonomous on the field. And I'm focusing on the SLAM localization, navigation, planning, and control part, and especially in challenging environments. And things I like, building things together with motivated people. This is how I grew up, I would say. I spent a lot of time in preparing for robotics competitions in my studies, for example, and still like to be in a team. Yeah, I really like to do software development and for open source projects. And I also like to travel, especially to conferences where I can learn something. Yeah, and recently I was, for example, skiing, and in the summer I like to do inline skating. Yeah, so that you know me a bit. Yeah, but this talk is not so much about me, but about the mesh navigation project, MeshNav. And here you see a video. This is yeah, essentially the product of a work that is 10 years old. So there was a PhD student in my lab, as I was a bachelor's student. He did his PhD. His name is Sebastian Pütz. And he started to build up this project in 2015. So this is about 10 years ago. And he started to use triangle meshes as representation of the environment, because he thought this would be like a smart way to do it. And yeah, you can do a lot of cool things with this representation. And this is what my talk is about today. I would tell you why this was, I would say, a good decision to choose triangle meshes for navigation in any terrain. So I will start to give a short overview about the theory and what is currently there in our tool set. I will continue giving you some insights about like design decisions, how we wrote our software and so on. This helps you perhaps to understand a bit how to maybe also write plugins or use it as a software developer. Yeah, and I will continue with all the stuff that is essentially required for successful navigation, that is localization and obstacle detection. And yes, there's a causal dependency. We will see about that later. Then I will continue with something we built up recently, that is a mesh MPPI, we call it, because it's a model predictive path integral controller considering the mesh surface. And I will end this talk with showing you some real-world scenarios where we have currently mesh navigation in use. So part one, the theory behind it. So this is actually an image my wife drew because I asked her, please draw me a cross-section of the map of an uneven environment. So this is our cross-section now, and we want to somehow represent this world with a map, at least the surface, so the green area. So what we get, so what you maybe know, are point clouds. So this is like the rawest form of data we get from sensors often, if you use LiDARs, for example. So one can think of, yeah, we just can use the point clouds to do navigation. But the problem here is, as you can see here, there are gaps between those points. So it's not only that it's hard to traverse from point to point because you have to sort them somehow. It's more about these gaps. So you can still traverse from left to right, but you make some implicit assumptions that there is a closed surface on it. So yeah, the problem here is the gaps. And if you have this point cloud here, it's 7 points. You can also describe another world with it. So it's like a bit ambiguous representation of the surface. And that's exactly the problem we have with point clouds. It's not so much about the traversal, but more like the gaps we have here. We make too much implicit assumptions. So yeah, one next representation would be something like voxel maps. It's like if you use standard enough 2D navigation approaches, you may know the like images with pixels. It's the same thing, but in 3D. But still here we have like from the design part, the problem that it's a bit discretized. Yes, so as you can see here, it's completely covering the world. So we cannot really find another world having the same representation. Yeah, but it's discretized. So what we came up 10 years ago, or Sebastian Pütz and in our lab, is using polygonal meshes. I'm pretty sure it's even older than 2015. But Sebastian tried to make it accessible to the community, to the robotics community. So this is like a cross section, and the polygonal mesh or triangle mesh is it's like the view from the side. So then it's a line essentially. As you can see here, a polygonal mesh is completely covering it, and it's very smoothly covering it. And you can see here that is that you can represent the environment using different resolutions as well. This is actually a cool feature we have using triangle meshes. It allows to have high resolutions when required, only then. So we can represent complex shapes arbitrarily with arbitrarily many triangles, while still represent flat areas by only a few number of triangles, which is a really cool feature because yeah, also we have come to that later, also because we have like an implicit connectivity here. We have some advantages when we want to traverse the navigation structure, which is required during many parts of navigation. Like we do global planning using, for example, A star, or do local trajectory planning using some model predictive controllers. And it's often required to traverse your scene representation. And this can be done using meshes in constant runtime because we have the connections already. Using point clouds, you would normally build a KD tree on that and reach runtimes of logarithmic runtimes. Or you create meshes out of your point cloud, and then you have, again, constant runtime. But then you have meshes instead of point clouds. So yeah, this is what we thought 10 years ago is like a very, very good feature of meshes. This would give like the opportunity to create a structure for even small robots with not so much computational devices on it, power, that we can still do 3D navigation with it. And those both points together build another property that is really, really cool if we want to do model predictive control. So especially these kind of, we have flat surfaces represented by a few number of triangles. I will come to that later, but you can start think about what property this might be. So meshes, we can do geometry-aware planning on meshes implicitly. Because meshes implicitly encode higher costs. So we collect higher costs over hills because the distances are higher, just by geometry. I have an example here. I will use it throughout my talk. Here you can see already costs applied to the mesh. So this is not only a visualization of the geometry, but here you can see in the, maybe you can see my mouse cursor. For example, if you want to drive over from one side to the other, the actual geometric shortest path would be a safe one here in the edge, in the corner here, and because it would not make sense to drive down and up again, just geometrically. So this is a cool feature, I would say, of using 3D. Yeah, but still, when you start here where the robot just stands, the shortest path is still through this abyss here to somewhere else where you don't want to drive. So we added something to also do cost-aware planning. So this is something we have to add explicitly via mesh cost layers, we call them. We already implemented something. So some layers are automatically generated by some analysis of the mesh surface. Here, for example, we do some analysis on the vertex height compared to the nearest neighbors, which is very fast because we have constant lookup times of the neighborhood. Also, we use normal differences, and heights in general to generate height difference layers, roughness layers, steepness layers, something that you can just select to have to use. Furthermore, we have some newer layers that are also helpful with some situations. For example, your robot has a certain height. Sometimes it just don't fit through a hole. And then you can have, for example, this clearance layer. It can say here my robot is 70 centimeters high, and then it marks the hole in red on the left. Further, you have like the standard inflation layer to have some, to keep some distance to lethal costs areas. Further, relatively new is the border layer, because sometimes you are not really sure if the border is intended. So if it's really over with your map, or if you just haven't measured anything there. So this is something where just you can go to your border of your map carefully, so that you're not falling down if it's an abyss or something. So yeah, and the newest one is an obstacle layer, where we can detect objects that doesn't belong to the map. So everything that is detected in our scans can be added to the map as dynamic cost layer. This is something I will tell you later throughout the talk, because this is needed to, so for this we needed to make some changes in the API. Yes, but as an overview, this is something, these are the layers we have. Everything is, yeah, we made a plugin interface for that, so that you by yourself can easily add your own cost layers. You can also add cost layers that encode like semantic information. For example, if you have like in your garden some beds, and your mom says no, you are not allowed to drive through the beds, even though your robot can or could. You could add some kind of semantic layers to avoid those zones. So this is, everything is possible here. You can keep the code in your own repositories if you want, because everything is plugin. So yeah, is a plugin with plugin lib. Yeah. And once we have those costs attached to our geometry of the mesh, we can start to do planning and control. So we have implemented essentially 2 planners right now, planners that not only compute the path, but also like a whole distance field. For example, Dijkstra is computing the all pair shortest path. And as you can see here, it's the Dijkstra itself, it's a bit, yeah, not so straight to the, it's because it's computing distances over the edges rather than over the surface itself. But in 2019, we came up, or Sebastian during his PhD came up with a better solution that created geodesic optimal paths using a continuous vector field approach. Yes. And then we have a global plan. And this global plan can also go on over different levels, I would say. As you can see here, once we have this plan and the vector field, we can use the vector field controller to execute the plan. And the vector field controller is already implemented, is also like the planners. These are plugins. You can also write your own controller or planner. But this vector field controller we already deliver with our mesh navigation repository to start with. And there it just takes the vector field into account and gives some control commands based on that. So, and the latest thing we added is, as I said, so first of all, you see some real world experiments with a small research robot, and we're driving like next to very dangerous abyss. So it could fall down, but it doesn't, just because of the cost layers we added. We added dynamic cost layers here for obstacle avoidance. And we added a modern predictive control to make the, so this is like very new, to make the motion more kinematically feasible. I will come to that later. This is the last chapter. Also, we have a lot of tutorials there, so check it out if you want. I I think we make, like, over the past half of a year, we made a lot of progress in writing tutorials. So also with real worlds map. So we scanned a lot of actual worlds, put them into Gazebo, and you can download them and check it out. So yes, and that was the overview of what we currently have. And now it gets a bit deeper. The part 2 is about the software insights. So this is something that was like, yeah, it was learning in progress for 10 years. As you probably know, when you're writing software, then you make a lot of things wrong. And I'm especially very proud that this little project is existing for 10 years. So yeah, and this is because we learned a lot. And one thing is what you already probably know as a roboticist: we don't want to reinvent the wheel. We look first and act second, like our robots are doing it. So in 2015, both polygonal meshes and robot navigation were existing. It was course 1. It was move base was existing. Polygonal meshes were existing like decades ago of that, because of computer games, from computer graphics. So this is something that was existing, and there was expertise already a lot. So this is so we also decided at some points to write our own data structures, but it showed that during the progress of maintaining and improving our software, it was in the end not a good choice, because in the end, computer graphics people do that all the time. This is a structure they are very familiar with. We shouldn't reinvent that. So this is why we decided to also not so we were brave enough to also include core structures when they are good, from the computer science community, from the computer graphics community, sorry. Even though it's a very core structure, and sometimes you don't want to have core structures as a dependency on other repositories, but it just doesn't make sense. It is what these people are very good at. So yeah, but what we really want to do is we want to let a robot autonomously navigate, perhaps with a low-end computational resources. This is why we chose in our design principles efficiency over simplicity, even though we would like simplicity. But yeah, if we had the choice, so if we had to decide, we would choose efficiency. We want to take the advantage of the robot's computing hardware only if available. So if there are many different computing units available, we want to use them if possible, like CPUs or GPUs. And we always want to keep in mind navigation is a small part of the robotic system. It's just a very, very small part. The robot has to compute all the time, all the craziest stuff while driving, perhaps. And we don't want to consume more power than is needed with our navigation software. From that, we made some design choices. First of all, we choose map agnostic and industry-proven navigation interfaces using move-based flex. I will tell you what move-based flex is in one slide later, I guess. We used established mesh structures for efficient traversals. Like right now, we're using OpenMesh/PMP mesh. So we're using PMP mesh, which is essentially a lightweight wrapper around OpenMesh. it's a core of OpenMesh, the mesh structure. And we were using it via LVR2 interfaces, which is just creating abstract interfaces over it to change it if we want to. So the remaining part, like the critical parts of such a navigation software, is raycasting. And raycasting in triangle meshes stays logarithmically because of the acceleration structures behind it. But still, we have to do it a lot, as you will see later. And therefore, we decided to also don't write this by ourselves, but use established software for that. And we use Intel Embry on the CPU, NVIDIA OptiX. If we have a GPU, NVIDIA GPU available and want to have hardware acceleration. Also, we have now a relatively new Vulkan implementation, and we triggered via Imagine interfaces. This is like a small software project I implemented during my PhD time to make the API as easily accessible as possible for robotics people. So MoveBaseFlex is the navigation framework we choose. It was developed 2014 or maybe even earlier. I'm not sure. Wasn't able to look that up fast enough before my talk. So it was developed by Sebastian Pütz at Magazzino. You probably know the company, and it's still in use there. And at Osnabrück University. In 2023, we migrated it to ROS2 and moved the code to Nature Robots. So the ROS2 version of MoveBaseFlex is now maintained by us, and the code is also by us. But it's still open source, and everyone can contribute. And it, as long as I maintain it, it will stay open source. So the features of MoveBaseFlex are like it has a strong map agnostic interface design. So MoveBaseFlex interfaces are just computer paths from A to B and let the implementation decide how to do that. Both action interface and the abstract implementation interface is map agnostic. So this means the action servers of MoveBaseFlex are triggering or invoking abstract function calls, where at first maybe no implementation is available, but yes, MeshNav implement those abstract function calls, abstract functions / classes, and this means once the abstract function call is called by the action servers of MoveBaseFlex, mesh navigation is triggered and uses a mesh map to find the path across the mesh surface. Yes, and this means as long as we can use these interfaces, these abstract function interfaces, we can reuse all our deliberation software we already have written, like behavior trees or state machines and so on, without changing anything. As well as MoveBaseFlex comes with unified error codes. So it has like predefined situations where things can fail during the planning process or the control process, and it also leaves some error codes for the implementation dependent errors. As well as it is, as I said, long used in industry. Right now it's also in use. So this is why we decided to use MoveBaseFlex there. And it's open source. As I said, as long as I'm the maintainer, it will stay open source. And probably also when I'm not the maintainer anymore. So I have created a small example what all this means. from a perspective of someone who wants to write a state machine. So this is an example we created because it has a map agnostic design. We created a nav2 connector for move-based flex. So you can just start nav2 and call the move-based flex actions, and they just passing the messages to nav2. So then we can use all the planners and controllers of nav2 in our favorite warehouse, as you can see here. Once we are driving outside, we can switch. We can switch to just by changing a string. So changing the action server, but using the same goal definitions, like the goal post definitions and so on. Get a path, exit paths, and so on. So I brought a small example. So this is a state machine or some kind of a state machine. There I created, so on the left side you see the mesh, on the right side it's the state machine, and I connect some things. So wait for pose, guess, then get a path, then exit path. So this is like the most basic state machine you would have for navigation, for the move-based flex action interface. And once my pose is drawn in Aves, the state machine is triggered. This is for the mesh part, and now remember how it looks like. This is the state machine for nav2. The same action interface, but we just changed the action server and the planner strings. So in this case, the planner is called nav2 planner and the controller is called nav2 controller. And the previous slide, it was mesh planner and mesh controller. And we can control the robot in another world. So, and this is this was the action interface side of things. So when you want to design a state machine or a behavior tree, this is important for you, but this is the code interface side. So as I said, move-based flex calls the abstract planner and the abstract interfaces, and these are two of many. I think there's also recovery behavior, but these are the most important ones for this talk. There's the abstract planner, and there is the abstract controller, and mesh planner and mesh controller just implements those abstract interfaces, but has additional information about the mesh map. As well as if you have this nav2 connector repository or package, it does the same, but has just passing the nav2 messages through. You can see, read more about this directly at the move-based flex repository, or just ask me. Yeah. So MeshNav also provides code interface plugins, as I already said before. So if you specifically want to write plugins for meshes, so like planners, controllers, or cost layers, you can do that. Examples are a lot of examples are right now in the code repository itself, because everything is a plugin implementation that we have there, like every mesh planner, every mesh controller, every cost layer. Also, we have some docs and tutorials about that, but not so many as I wish to have. Yeah, still. Okay. Yeah, looking at the clock, we'll have to accelerate this a bit. But for successful navigation, we need a localization and obstacle detection. So, and a map. We need a map. This is the first thing we need. So for the mapping side, there is right now, or the last years, emerged a lot of SLAM software. In this case, I will show you an image about Glim. We like to use Glim, and then you just drive around with the robot, put it into Glim, see if it is like if we get consistent maps, point cloud maps, put it into some tooling of our LVR2, and LVR2 can create meshes out of point clouds. So this is so we documented this very well in our tutorials. So if you're interested in that, just read the tutorials. Otherwise, call me or something. Yeah, and this is the result. We can get, so this is the same world, but now we have triangles instead of points. But there's also research about direct mesh SLAM. So SLAM that directly produces mesh maps. I also used some of them. Yeah, so there's a lot of things out there. If you have this map, I, during my PhD, built some tools about localization in those mesh maps. I called it RMCL. This is the package name or the repository name, and also one of the tools names. I started with just doing registration of range sensors against prior mesh maps, called it Mesh ICP, and ended up with doing raycasting Monte Carlo localization, about this later. And we computed the sensor model via raycasting in a virtual scene using our Imagine, again, with established libraries that are already there, and it's very, very fast. So you can see here, for example, the registration part of the localization. They'll draw an initial post guess, and the robot is corrected towards the map so that it's, yeah, after that it's localized using LiDAR scanners, for example, but depth cameras are also possible, as you can see here. It also considers the motion of the robot. Yes, we can also use 2D scanners in combination with our wheels, for example, which is quite useful, or any combination of any sensor we have. Yeah, and it's, since we are using these libraries like OptiX and Embry, we can also, so we have a really fast runtime, so really fast. As you can see here, it's an example of the Muran datasets. It's 21 million vertices and 12 million triangles. It covers an area about 1,000 times 700 meters, and still we can reach real-time localization even on CPUs. We couldn't do that if we started to implement all the things on our own. So this is, Intel did a very good job on Embry. Yeah. Next thing I did was a probabilistic localization. I also talked with you guys about Gerardo. This is currently still a work in progress, but it's working pretty fine. We can globally localize there using particle filter approach, and yes, more on that. Just look it up on GitHub. It's everything is available. What you can see here is available online. And the cool thing is, if something is uncertain, it stays uncertain. So this was a thing I was, yeah, very particularly interested about. If something converged, then we started to estimate a covariance around it so that we can use it for other software that relies on unimodal state representations. Uncertainty. Once we are localized, now we come to the obstacle part. We directly have correspondences with the map. So because we already computed it. So, and as soon as we have them, we can just apply some filtering. As you can see here, every point that belongs to the map is now filtered out. And so we call the points belong to the map are expected points. But there are also points that are not expected given our prior map. And this is, for example, the people. One of them is me, by the way. Yeah. Yes, and you can use them and project them down, and then you have and can create a dynamic cost layer out of it, and that's it. It's very fast, as you can see here. It reacts directly when something is hit, and yes, but there comes the problem. We had to change some things. Normally, you have like a large map, and you hit one specific obstacle with detect one specific obstacle, and then you start to create some inflation around it. So this is what you want to do. But if you recompute the complete inflation of everything, then it takes some time, and then we have like reaction times that are too high to react to certain changes. So we came up with the dependency tree of how we compute our layers. So we have the height diff layer, the steepness layer, the roughness layer working on the static part of the map, are combined with an average combination here, so just makes an average of the costs. After that, an inflation is computed on the static part, and this is the left part of the tree that stays static, because this is only because of the static, it's only about the static map part. On the right side here, this is something that is computed a lot. So if you have the obstacles computed, they are inflated, but only the obstacle vertices. And this is something, this reduces down the latency a lot. So this is in the end combined so that we can use it for our next thing, and this is MeshMPPI. MeshMPPI, there we created something to create kinematically feasible control commands for our robot by rolling out trajectory on the mesh first. As you can see here, just falls down or rolls down the slope. We collect costs along the way, and then we do it similar to what's implemented in NAV2. So doing path integral estimation, so sampling-based optimization, and select the trajectory that is best with the path integral. Yeah, so as you can see on the bottom. Yeah, and now I come to the point of slide 9. Together, both points implicitly create a very nice property that helps us with MPC and so on. A mesh can accurately represent the environment with a few triangles on flat surfaces, many triangles on uneven surfaces. Usually, flat surfaces are considered geometrically safe. Uneven surfaces are considered geometrically dangerous. So with a fixed number of traversal operations, we can overcome greater distance on flat than on uneven surfaces. Now an explicit example for model predictive control. Triangle density on the ground of the forest is 3 times as high than on the street. So on the street, we can reach 3 times greater horizon lengths for the same number of traversal steps for sampling-based MPCs. This means inversely that we can drive faster or more safety with the same safety for the same number of computations on flat areas, which is usually desired, I would say, because you're driving on flat surfaces. Usually you drive faster on flat surfaces than on uneven ones. In the end, this is something, so this is the final result. Same environment, we draw goalposts, and now it takes part, so it computes the path, and it with the model predictive control, which is black, the optimal trajectory, it's going near the close to the path, but also considers the costs of the mesh. So as you can see, it bends around the corners where it's red. Yes, and then it's at the goal. We also made some tests with this. We created this in summer to some other approaches, some more fair than others, I would say, because NAV2 is like a 2D approach and it just fell down because you cannot really good represent the cliffs and so on just by doing SLAM, 2D SLAM. So we created the 2D map by using 2D SLAM. Yeah. So, and this is the last part. So currently we have like a small study group of students and they used it in the basement, the mesh navigation or mesh navigation. There the robot is driving through a door and detects, hey, the door is closed. In my map, it's open. So, and this is something really cool about the 3D approach as well. Even though you have flat ground, you can have a rich understanding of your world. It's like the same thing. Blue points are points that are unexpected, so obstacles. And in this video, you see that the door is closed. In the map, it is open, and the red dots are marking points where you unexpectedly the map is wrong. So you would scan through these points in your map. And these red points would mark an area where you can start to adjust your map a bit. So systematically change your map. We haven't done it yet, but it's, I mean, the filters are there. Yeah. Also at Nature Robots, we like to use it to encode some information about the about uneven terrain. Here you can see our Lero 2. So this is version 1 before. Right now we have Lero 3 built up, and here you can see mesh navigation in combination with a waypoint graph that is used for planning. And yeah, so it drives over some beds. You can also see here some sensors that are used, like GPS and an Auster laser scanner. Also some solar panels on top to increase a bit the battery capacity. It can also drive through mud, as you can see there. Yes. Yeah, the 3D model is still the Lero 1. Yeah, this was a demo day. We hadn't had any time to create the new 3D model there or to include it. And now it's driving back home. So yes, to its garage. And that's it. Here are the worlds again. You can find in the tutorials. And the robot is driving towards you. So if you want to help with this project and keep it alive for another 10 years, feel free to contact me or just contribute. Like, I would be happy to see people contribute to this project in any way. So it could be something like reading the tutorials, reading the documentation, adding something to the documentation, testing this thing in real world, finding bugs, anything you want to do would help us. So you can contact me anytime, and that's it from my side. Thanks for having me.
Okay, thank you very much, Alexander. That was really interesting. We are open to questions. Anyone who wants to ask a question, please use the QA section of this meeting. I will get started by asking you, what's the what's the storage cost of this kind of representation? You mentioned that you wanted to be able to use this in particular in smaller embedded systems. Do you need what's the largest map that you have ever mapped? What was the cost of that in terms of representation when you wanted to use that? And do you need any strategy for larger maps to be able to use them?
That's a good question. So right now I'm thinking, so even though like if you're thinking of standard 2D navigation and you're using maps, so like grid maps with 5 centimeter resolution, I think that you're reaching limits with that as well. So especially if you have these environments, when I go back here, there are triangles way larger than a 5 centimeter cost map. As you can see here, these triangles are larger than the robot itself. So the only problem comes from the additional dimension, I would say. So it still needs more memory because we have an additional dimension. Otherwise, I think it consumes less memory than existing 2D approaches. If we had if we discard the additional dimension, yeah, still. But so memory-wise, I would say it's still good. So right now, I would say like a half square kilometer maybe is okay. Also on low-end hardware. And then you have to do map changes. So change the map, I would say, at borders. So creating spawn zones or something. So do a bit of chunking. It's also possible. So as I said, you can also switch between 2D and 3D navigation approaches using move-based flex. So you can also switch between different 3D maps. Yeah.
Okay, perfect. Thanks. Tomas is asking, we did some testing with point clouds to mesh map and had really bad results. Did you learn anything specific to make this conversion succeed? Does it always succeed?
Yes, there are many points. So this is another part we did a lot in our research lab. It's creating meshes from point clouds. This is why I grew up with this mess, I would say. Yeah, one thing that is very good is if you use implicit maps, so like TSDF maps, because you erase a lot of things away, like a lot of noise. So if you have software that can do that, this would be, so this usually creates consistent meshes. Yeah, if you don't have that, so first of all, TSDF-based approaches tend to consume a lot of memory. So this is a problem of them. They tend to create good meshes, but consume a lot of memory. This is like implicit map generation. There are also some from Uni Bonn, I think. I forgot the name, but they also do some neural mapping and also get some meshes out of it. So neural implicit mapping. Good meshes from that. If you don't have that, if you don't have much memory and just have a point cloud and want to get a mesh out of it, then it helps to have the original scan position of the point. So the angle from which you measured the point, which you can use to flip normals. Because in Open3D, you normally, so if you have like just the point cloud, you start to compute normals, so surface normals, and take them as granted after that. And around that, you can start to create triangles. So, but the normal computation part is very tricky if your point cloud is, if you don't know from which angle you measured the things. So this is something, if you read our tutorials and read the part about GLIM. So first use GLIM to create a point cloud. This is only half of the truth. You use GLIM to create a point cloud and a trajectory. Then you use the second tool of us, which is also documented there. that creates normals and flips them towards the point of where you measured it, so where the scanner is in the trajectory. And then you get consistent normals, and once you have them, everything gets easier. Then your meshes get better. So then there's another point. Then if you have a scanner that tends to have a lot of noise, it gets worse as well. So yeah, it stays a tricky problem, but mesh navigation itself don't want to include this problem because we know how hard it is. Yeah, hope that answers the question.
Perfect. Thank you very much. That was really interesting. Marco asks, you mentioned that you use CG meshes algorithms as a guide. Based on the problem you solved, were you able to simplify the data structures?
Could you repeat the question? So about the data structures.
Sure. Marco, do you want to do the question yourself?
Yeah. To add a little more context, sometimes the computer graphic algorithms has a lot of extra information to do some operation. For example, you have a list of the near triangles. In this search of the data structure, were you able to remove some not used information for your case? To simplify a little bit the original data structures?
So you mean that if there was information that is not really useful for his particular use case, if he found it useful to not to use that?
Correct.
So not that I think of. So right now we are taking like mesh buffers from ply files, for example, or OBJ or whatever we can load. This is just an index buffer and a vertex buffer. Then it's converted into half-edge meshes, perhaps. This is just the connection between those. OpenMesh has algorithms working on these half-edge meshes. We don't use these algorithms. We just use the data structure. So it's just the pointers connecting between the vertices. I don't think there are like any additional attributes we had to cut away explicitly. But if you're interested, I can look it up and then you can contact me later or something.
Okay, we are a bit over time, but I have one more question, if you don't mind. You mentioned that you can deal you have cost layers, and you have in particular one for dynamic obstacles, right? And you show this basically adding a cube in the environment. Can you deal also with negative obstacles, such as, for instance, someone dig a hole in the ground in front of you? Can you also detect that difference against the map, and will you deal with that as in your cost map as well?
So right now, not with the current approach. But sorry, I'm not sure. Maybe we can. But so I go to the one video I showed you. I think it's with the door.
Yes.
This one. So right now the dynamic obstacle layer just takes a point cloud as input, projects it down, and creates costs. So we could also change the input or create another dynamic obstacle layer, a second one, takes the red points as input, project them down. So that like this we could perhaps fill a hole, but not geometrically. For that, we should do the systematic map updates. So this is something we're actually working on right now. That we don't want to do these systematic map updates. So this is something we push the responsibility away, but we want to have the possibility so that others can change the map, and that is considered like geometrically. So it should be possible right now, but we don't have any mechanism for that others can use it or change it from outside. Yeah.
Okay, perfect. Thanks. I think there are no more questions, so I will thank you for being here. It was a really interesting talk. I'm looking forward to seeing how your projects move from here.
Thanks a lot.